Welcome to the Explainer. Today, we are diving into a programming concept that can feel a little bit like a magic trick. It's called recursion, and we're going to pull back the curtain and show you exactly how it works.
I mean, that's really the big promise of recursion, isn't it? It's this powerful and honestly pretty elegant way of thinking about problems. The idea is that the solution to a big task actually depends on the solutions to smaller versions of that same exact task. It sounds a little circular, I know, but stick with me, and you'll see how it all just clicks into place.
You know those Russian nesting dolls? Think about that. To open the whole set, you open the biggest doll, and inside is a smaller, identical one. You just keep doing that until you hit that tiny little doll in the middle that won't open. That's your stop sign. In programming, we call that the base case. So a recursive function is basically a function that calls itself over and over until it finally hits that one condition that tells it to stop.
Okay, so theory is one thing, but let's actually see this in action. The best way to get your head around recursion is to just trace its path. We're going to start with a super simple task and just follow the logic, step by step, as it builds what's called the call stack.
Here's our goal. We want to print the name Raj 3 times. To do this, we'll use a function that takes 2 numbers. First, there's I, which is our counter. It'll start at 1. And second, there's n, our target, which is 3. The function's job is to call itself until that counter hits the target.
So here we go. The first call is f of 1, 3. The function wakes up and it checks its main condition. Is my counter, I, bigger than my target, n? Is 1 greater than 3? No. So it does its job. It prints Raj, and then right away, it calls itself, but this time it bumps the counter up to 2. It's basically saying, okay, my part's done, now it's your turn, f of 2, 3.
Now, f of 2, 3 is running. And it asks the exact same question. Is 2 greater than 3? Still no. So it does its thing, it prints Raj for the second time, and then it passes the baton again, this time calling f of 3, 3. Each one of these calls is getting stacked right on top of the last one, just waiting for this whole chain to finish up.
All right, we're at f of 3, 3. Is 3 greater than 3? No, they're equal, so the condition is still false. So we print Raj for the third and final time, and then we make one more call, f of 4, 3. And this next step is the most important one.
And there it is, the base case. When f of 4, 3 runs, it checks. Is 4 greater than 3? Yes, finally. That yes triggers the return. It doesn't print, it doesn't call another function, it just stops. This is the stop sign that keeps us from getting stuck in an infinite loop, and it allows that whole stack of functions that have been waiting to finally complete and close out. So what does this all mean for performance? Well, because we made n different calls that each had to wait around in memory in that call stack, we can see that both the time it takes and the memory it uses grow in a straight line with our input, n. In computer science, we call this O of n complexity.
Okay, so we've got the basic downward journey down. Now let's see how a tiny change can completely flip the script.
Check this out. See how we control the flow? To print from 1 up to n, we start our counter at 1 and just add 1 each time. To print from n down to 1, we literally just reverse the logic. We start at n and we subtract 1 each time, with a new stop sign that tells us to quit when we get below 1. It's the same exact structure, just running in reverse. Simple, right? But what if we made it harder?
This, right here, is where recursion gets really cool. We're about to introduce a little puzzle that seems like it should break the simple logic we just learned.
Just let that sink in for a second. We want the output to be 1, 2, 3, but our recursive function is only allowed to count downwards, 3, 2, 1. How? How is that even possible? It feels like we're being forced to do our work in the completely wrong order. This is where we unlock a whole new level of thinking about this stuff.
The solution lies in a really neat concept called backtracking. You see, so far, we've only focused on the work getting done as the functions are called, on the journey down. But the real magic can also happen when the functions are returning, on the journey back up the call stack.
So the solution is actually way simpler than you might think. It all comes down to a one-line change that has a huge impact. Instead of printing before we make the next call, we're going to make the recursive call first and only print our number after that call is completely finished. Let's trace it and see what happens.
Okay, so we start with f of 3, 3. It checks its stop sign. Is 3 less than 1? Nope. But now, instead of printing, its very next move is to call f of 2, 3. So f of 3, 3 just hits pause. It's holding on to its value of I equals 3, and it's just waiting. And this just keeps on going. f of 2, 3 immediately calls f of 1, 3. Then f of 1, 3 immediately calls f of 0, 3. And get this, nothing has been printed yet. We just have a stack of 3 functions, f of 3, 3, f of 2, 3, and f of 1, 3, all patiently waiting for the calls they made to come back.
Finally, f of 0, 3 gets called.
It checks the base case. Is 0 less than 1?
Yes. At last, the stop sign is hit. It returns immediately. This is the trigger. The whole downward journey is over, and now the return journey begins.
So where does it return to? To the function that called it, f of 1, 3. Now that function can finally move on to its next line of code, which is print I. And what was the value of I inside this function? It was 1. So the very first thing that gets printed is 1. And the stack just keeps unwinding. Once f of 1, 3 is done, control goes back to f of 2, 3. Its big recursive call is finished, so it gets to print its value of I, which is 2. Then control returns to the very first function we called, f of 3, 3, which at long last gets to print its value 3. And just like that, we printed 1, 2, 3 by counting down. Pretty cool, huh? This quote from the source material just sums it up perfectly. By putting the action after the recursive call, you guarantee that the deepest function in that stack, the very last one called before the stop sign, is the first one to do its work. You've completely reversed the order of execution without ever touching the counter. So let's just quickly boil this all down to the 2 most important ideas from this explainer, and then I'm going to leave you with a final challenge to try on your own. Okay, first, every single recursive function must have a base case to stop. This is not optional. Without it, you just have an infinite loop. Second, when you do the work is everything. If you do it before the call, things happen sequentially on the way down. But if you do it after the call, well, that's when you unlock the power of backtracking on the way back up. And that brings us to your challenge. Now that you understand backtracking, how would you flip this last problem? How would you get the output 3, 2, 1? But by using a function that can only count up from 1 to 3. Think about where you'd place that print statement. It's a great little puzzle to really test if this all sunk in. Thanks for tuning in.